Yeah, good evening, Muthu. Good evening, everyone. I guess am I audible? And you can see my slides also, right? Okay, fine. Thanks, Muthu. So, good evening, all. Welcome to the week of our problem solving discussion for the course NOC 22 C68 Ground Improvement, which is a NPTEL course. The course is currently being tutored by Professor Dilip Kumar Bedia, who is who is head and professor from Department of Civil Engineering, IIT Kharagpur. Myself, Rituraj Singh Sujawat. I am Prime Minister's Research Fellow in the Department of Earthquake Engineering, IIT Roorkee. So those who have joined right now, this session is basically based on where we are going to solve some of the sample problems, which is going to help you in solving the assignment problem related to the NPTEL course. And also, if you are having some any technical or non-technical query with the course, we can discuss that also, or any other sort of query related to the course, we can discuss here. So this week was basically revolving around the dewatering and the drainage technique only. So where we used to go for the dewatering. So if you see, like here some of images are there. So whenever groundwater table is not at a greater depth and it's available at very shallow depth, but we want to do the construction because we want to lay the foundation or the shallow foundation at a particular depth. So if groundwater table is available at very shallow depth, so it becomes very difficult to do construction here because it's both not appropriate for labors also, construction practices also, as well as like the strength and the settlement problem related to the soil will also take place if the groundwater table is available at very shallow depth. So that's why we are going for the dewatering technique. So where we are basically lowering the groundwater table with some of the methods which basically categorize under the dewatering. We also take the help of the drainage to, like in the drainage, we are basically providing some drainage path so that the water will pass. uh, we are giving a pathway for the water to pass, and that will basically help us in lowering the groundwater table. So here is one of the picture of the dewatering technique. So as you can see, like we want to do some excavation here, but if the groundwater table is available at very shallow depth, so it will interfere with our construction practices. So what basically we are doing, we are lowering the groundwater table with this dewatering technique, where we are basically applying the pumps to which will create a height difference and it will lower the groundwater table. And with these well points we are basically removing the water, and we are transferring to the nearby water bodies, and it will further help us in better feasibility of the construction practices. So if you want to see how the dewatering used to take place at sites, so dewatering can be further categorized into three parts. Like you can do it from the sumps and trenches. So if the water table is at the surface only, so we can basically take help of the sumps and trenches, where we are just apply the pump at the where we apply the pumps or pipe at the surface, and it will create a height difference, and the water can be transferred from the top surface to the nearby water bodies. We can also take the help of the well points, where if along a ground we are having various, like the water table is at a particular depth, so we can't go for the sumps and trenches. So there we will apply a pipe, and these pipes will further connected to the uh, for subdivisions. These subdivisions are lowered into the ground, which will basically be, like if you check, so this is the well connection example. So here you are having a main pipe, and then you are having the sub pipes. These sub pipes are embedded into the wales, and these wales are basically transferring the water from the uh, some groundwater table, and it will transfer to the main pipe, and this main pipe will further transfer the water to the nearby water bodies. Also, we are taking the help of the electroosmosis to transfer the water from certain depth to the nearby water bodies. So here we are basically creating a potential difference between the soil particles. So once, since the water, you know, it's a positive particle, so as you will apply a current to the cathode, so these water particles will try to move from positive to negative, and it will create a hair difference, and this water then can be further transferred from the well point, and the same procedure will be followed for the dewatering. So anyone is having any problem with the dewatering, or you want to discuss something about the dewatering, let's bring it on. Okay, then, like if no discussion, then like let's move to our problem solving round. So let's start. So if you have gone through the lectures or the videos of this last week, you can solve this question. Even though you had not gone through that, like we are going to discuss these questions here, so that's fine. So first question is, like, this is a picture of a typical cross section of a groundwater. So this is an unconfined aquifer. So basically your water table is not restricted to any impermeable layer, or your well is not restricted from any impermeable layer. So in this you need to show the level A. So what level it represents, whether it's phreatic level, piezometric level, both A and B, or none of the above. You can keep your answer in the chat box, or you can unmute yourself and answer, but better to keep it in the chat box. You guys are able to see the slides, right? Hello. Okay, thank you. So here is the first question. What water level it represents? If you are having your notes, you can go through them, check it in there, and give the answer. Anyhow, we are going to discuss that. So whether it's phreatic level, piezometric level, both definitely cannot be the option. Yeah, Muttu. It's option A. So basically, this is the phreatic level. So the instantaneous position of the groundwater table at any time instant, like it will be called as a phreatic level, and the initial groundwater level is basically the piezometric level, you can say. Going to the next question. In electroosmosis method, when we apply a direct current to the electrodes, in which direction the soil will move? Here are your four options. Just pick one of them. If you have any doubt, just unmute yourself and you can ask the doubt. Not a problem. So, yeah, Chandravir, it's travel from positive electrode to negative electrode. So, we have discussed earlier also. So, if you want to see, so this is a typical your soil cross section. So, if you and at a plan view, if you see how these electrodes are distributed, so this is the view you can see. And if you take a cross section at a point, like this is your toe of the slope, so it's here. And if you take a typical cross section at section A, so this is the view you can check. And here, if you take a further cross section and if you want to see the elevation view, so this is the part. So whenever you will apply current to the electrode, so since water particles are basically carrying the positive charge, so these water particles will try to move to the cathode here. And as soon as the water will move from to the cathode to the negative electrode, you can basically take the help of some pump, or you can transfer the water from here to the top surface. So basically you are lowering the volume of the water in this region, and that will help you in lowering the groundwater table. I guess it's clear with everyone. Any doubt in this? Okay, then let's move to our next question. So among all these three methods mentioned here, which method you can use to control the groundwater? Basically, you want to lower the groundwater. So which method you are going to go? So again, yeah, if you have gone through your lecture notes, so all the three methods you can use for the controlling the groundwater table. So if we can see, so basically if you are having three methods are there to control the groundwater. So one is the barrier, second is the dewatering. About dewatering we have discussed in detail in earlier. About the drainage, we are going to discuss about that in the next session. With the barrier, if you can see, so if we are having any pavement or the road constructions going on, so if you want to restrict your water to enter into the construction components or any of the nearby components, so you what you can do, like you can apply some damping barrier or any impermeable membrane which can basically restricting the moisture of water from entering from the soil to the construction components. So this is the barrier you can use, and this basically you can see in the pavement or in the road constructions, or even in some other parts also where the uh, construction size is means at a particular cross section the construction size is not that large. So in that case you can go for these barriers. And dewatering we have discussed, like we are applying some pumps, with the help of the pumps we are removing the water. And drainage, basically we are creating a path along any construction or any structure, so where we are providing a path for the water, an alternative path to the water, so it won't lead to some failure criteria into the soil. So let's have a better discussion about drainage in the next session. So yeah, if you would have gone through the different type of drainage, uh, which type of drainage this diagram represents? Guys, please feel free to ask the questions and have a discussion about any topic. We are here for discussion only. Yeah, if you can say
for the
something.
some. The பேசாமல் சவுண்ட் வந்த மாதிரி இருந்தது டிக் சவுண்ட் வருதுல்ல
I guess.
ம் இதை அட்ஜஸ்ட் பண்ணுமா ம் சவுண்டு கீழே டிக் சவுண்டு நல்லா கேட்குதா பாருங்க
Do you
ஹையில்
have any
இருக்கு
doubt
கொஞ்சம்
about the
இருக்கு
new name, the Living God?
அதான் டிக் சவுண்டு கேட்குது
Okay. Yeah. So the answer for question number 4 is payment trend. So definitely this is the cross section of the payment you can see. So whenever we are having some water table available at a certain depth and near the payment region, and if the water is trying to enter from the lower part to the pavement, we are basically providing a drainage path, which can which is basically stopping the water from entering into the pavement components or like the sub surfaces of the pavement, and it will further help us in keeping the intact strength of the soil or the what we can say the subsurface layers of the pavement. So I guess it's clear with everyone. Any doubt in this? So like other type of drains, if you can see, you would have seen in the lectures also. So this is a trench drain. So in any trench or in the pipe cross section or circular cross section into the soil, we are basically providing some trench. So the pathway for the water we are basically providing through the trench, and pavement drain we have already discussed. And if we are having any retaining wall, so along the retaining wall, you can basically provide a drainage path here as shown in the dash line. So it will basically provide a water like passage for the water, and it will further reduce the lateral pressure which will be acting from the soil or from the water, this hydrostatic pressure from the water to the retaining wall, and it will increase the strength or it will reduces the force on the retaining wall. Also if you see the dam or the embankment dam or the chimney drain, like this is the chimney drain we used to say for the dam only. So if we are having any embankment available, so this embankment the lateral forces can be further reduced if you provide some drainage path here like along the dam cross section. And also if we are having the some slopy region, so the water in the slopy region will from try to move from the positive to the negative, sorry, from the higher region to the lower region. And if in some way if you provide some drainage path in between some particles or some stones or gravel cross section, so that will help us in removing the water through with the help of this, and your failure of the slope will basically be prevented. And you can also take the help of the vertical drains. So if you are having like these are the gravel column we can use here. So this is your embankment. So once this embankment is capped onto the soil, so the soil will get compressed and the water uh, in the soil will try to access through these gravel columns. And with this the help of the gravel columns or the drains, you can basically again move your water, and with the help of some pumping techniques you can remove the water here. So, this technique is basically used in the soft soil. So there you can establish the gravel columns, which will further create a drainage path for the water, which will be generating to the excess pore water pressure. Any query in this for the drainage? Okay then. So that was all about the theoretic. Okay, we are having one more theory question. So the fifth question is, to maintain the bottom stability of any excavation, uh, what should be the condition? Okay, okay. Anyone else was facing problem with that? You guys were able to see that drainage question or the discussion about the drainage, right?
Yes, sir.
Okay, okay, Tushar. So we are having two types of answer, A and C. So if someone want to come forward and like give the reason why you have mentioned these options. No compulsion, just if you are willing to come and discuss. Why we should maintain the bottom stability of excavation and how we can do that. Oh, what is the minimum condition to maintain the bottom stability of excavation? So yeah, let's have a discussion on it. Yeah, it is a minimum requirement. So let's see the figure, like then it will be a better discussion. So yeah, overburden stress above sand layer should be higher than the uplift pressure. So why it's so? So this is the typical cross section of a ground. So if you see, like if we establish a well here, so if we establish a well here, and if you are having a two types of layers, for example, the above layer is the impervious layer, and the below layer is the pervious layer, and it's having the uh, moisture or the water we can say available in it. So this well will basically represent how much water head is present. So if your water head, which is basically the gamma w into delta h plus z, if gamma w into delta h plus z, if this water pressure, this is basically representing the water pressure. So if this water pressure is is greater than the overburden pressure, so it will lead to a failure condition for the soil. Why it's so? Because here your uplift pressure will act, and this uplift pressure is basically equal to gamma w into delta h into z, and the overburden pressure is acting here, which is equivalent to gamma z. So if this uplift pressure is greater than the overburden pressure, so it will basically lead to the failure of the soil. So keep in mind, whenever you are doing the excavation, your excavation should have the overburden pressure in such a manner such that the failure due to the uplift pressure won't take place. So for example, if you are going to excavate this much amount of the soil, so definitely your overburden pressure will get reduced and your uplift pressure will tend to try tend to failure the your soil here. So that's why if you're going for the excavation, you need to check for the lowering of the water head also here, so that an equilibrium should be maintained between both equilibrium or your overburden pressure, like the both conditions should be permissible, but your uplift pressure should not be greater than your overburden pressure. That should be the minimum requirement. So yeah, so your overburden pressure should be greater than your uplift pressure, or both can be in the equilibrium also, but that is a critical condition, so better to keep your overburden pressure higher. So any problem in this, any query? Yes. Okay, no query, then we can move to the next question. Just try to solve this. Yeah, who is this? Come inside.
Sir, Tanay sir, sir.
Come sir is not here.
I wanted to meet him actually.
Yeah, you can call him, like right now is not available. So yeah, sixth question is, for an unconfined aquifer, total required discharge is 0.0845 meter cube per second. So the number of well required when each well discharges 0.0056 meter cube per second. So yeah, basically you need to calculate the number of wells. So the total required discharge is given, for each well the discharge is given. So I guess it's pretty clear. You can give the number of wells which will be required. So yeah, let's check with the answer. Yeah, so the answer is 15. So basically you just need to, like, let's solve it here. Number of whales, so total required discharge is 0.0845 divided by 0.0056, and I guess it's the 15. Yeah, so basically 15.0809 which can be approximated as 50. So yeah, I guess it's clear. Any query in this? So let's move to the next question. So next we are having a design problem with the dewatering system. So just read the question. At a site, you are having the rectangular area which is 220 meter by 160 meter, and it's up to depth of 15 meter. You can see the cross section view. The existing groundwater table is at 6 meter. Below the ground surface is 30 meter thick gravel with a permeability of the 6 into 10 raised to the power minus 5 meter per second. So this is the gravel column, and this is the rectangular area. So this is a plan view, this is the elevation view. Your water table is currently available at the depth of 6 meter, and your basement basically which you want to design is having a embedded depth of 15 meter. So you want to lower your water table by 1.5 meter. So right now it's from the surface it's 6 meter, and you want to lower your water table such that from the basement bottom it should be below 1.5 meter. And you need to use the deep wells definitely for the unconfined condition to dewater the site, and you are having the 200 diameter deep wells. So this is the C dash value given. So I'll show you the questions, just note down the data. So if you would have noted down, like, anyone want more time in this? So let's have questions here. So first you need to calculate the equivalent radius of the excavation area. So right now it's given as a rectangular cross section. So once you will convert into the circular cross section, what should be the equivalent radius? Any answer, guys? Okay, let me solve it for you. So right now you have a cross sectional area, so it's having a total area of L into B, and you want to convert it into the equivalent circular area, which is having the pi r square. So length is given, I guess, 220, into breadth is given 160. So to get the equivalent r, you can basically divide it as a 3.14, taking r as this. So I guess the equivalent radius is 105.8 meter. So what you are doing basically, if you are, this is the rectangular area, so for the better calculation you are converting this rectangular into the circular cross section, because the well basically are in the circular. So if they are like pumping the water, so the influence area which is going to create around this circular will be the circular only. So this rectangular area we need to convert into the circular cross section. So the equivalent radius for calculating this circular area can be done through this length into breadth equals to pi r square, and you will get the equivalent radius. So I guess it's clear. Anyone is having query in this? Muttu, Tushar, something?
No, sir.
Okay, good. Let's move to the next question. So you need to evaluate the influence radius. So once you are like extracting the water through the well, how much radius or how much area it's going to influence. So the radius of that influence area you need to evaluate. Okay, so 1 second. Do you want me to show the total data, Muthu? This is only, right? Yes, Hemant, please.
Yes, sir, please.
You want to ask something, Hemant? Kumar, Hemant?
Yes, sir. Please show me the whole data, sir, please, for once.
Okay, yeah, fine.
Thank you, sir.
Yeah, Muthu, you want to see something?
It's okay, sir, now.
Okay. No, yeah, it's fine from your end, Kumar, Hemant. I'm asking from
Thank
Muthu.
you, sir.
He is asked. Okay, sir. Okay, then let's move to the eighth question. So, evaluate the influence radius. So C is the answer Muttu has given. Any other answer? Muttu, like you want to convey something? I'm not able to interpret. Logical think at this level. Okay, guys, let me solve it for you. So, for influence radius is basically given with the help of the formula C dash HW naught minus HW into K. K is your root K. K is your permeability. HW, like for example, this is your initial water level. So the depth from the bottom impermeable layer is basically the HW naught, and till the point you want to lower your groundwater table is the HW. Radius of excavation is 1 point. Okay. Yeah, Muthu, thanks. So, like if C dash, you know, it's given in the question is 3000. HW naught. So, if you just see the initial cross section, let me copy it for you. So yeah, so this is your initial. So here, if you can see 30 minus 6, so HW naught, you know, can be given as 30 minus 6, 24 meter. So your datum or your reference region is this. So from here you are checking how much is the height of your groundwater. So HW naught is the 24, and now you want to lower till here, like 1.5 meter from the base of your basement. So HW, if you want to calculate, so total is 30 minus 15 meter, the embedded depth of the excavation, minus 1.5. So the total is 13.5. So here it is 13.5 into root K. So permeability of this region, because we are evaluating the influence radius of this part, so it's 6 into 10 to the power minus 5. So 3000 24 into 10 raised to power minus 5. Just calculate this, how much it is.
Okay, sir.
Yeah. Okay, Mattu. Let me rewrite for you.
It's 189, 1.89, sir.
How much?
1.89.
Is it? One second. Actually, sorry, it's root k.
Sir, value is coming 1.89, sir.
Yeah, I got it, but here it's root
So
k.
that there's a root, sir, impermeability, perhaps.
Yeah, yeah, yeah. That's okay. So
Okay.
let me write it in white ink like once. Sorry.
Sorry, sir.
So SW note it's 24 minus, sorry, 30 minus 6, 24 meter. SW is 30 minus 15 minus 1.5 is 13.5 meter. So radius of influence is given by 3000. SW naught 24 minus 13.5 into root k. Root k, I guess it's 6 into 10 raised to the power minus 5. Now calculate this. How much is it? I guess
244, sir.
yeah. So it's 243.9, closer to 244 you can say, and yeah. So the answer is 243.9. So option A is correct. Any query in this? How we got it? No problem, Mattu.
No, sir.
Yeah.
No problem, sir.
Okay, thank you, Mattu.
Yes, sir.
So let's move to the next question then. If so, the total required discharge. So again, this is the unconfined condition. So your water is basically coming from the lowering of your groundwater, and there is no impermeable layer around your well. So the formula corresponding to that, like what with like how we are going to calculate the required discharge. I'll give you the formula. So, or you want to try it? Okay, let's have 2 more minutes. Yes, we are running short of time, so let me solve it for you. So since this is the unconfined condition, so the total discharge can be calculated through QW is basically pi k HW naught square minus HW square divided by ln radius of influence minus your initial bore hole means initial well radius. So pi into 6 into 10 raised to the power minus 5 HW we had not calculated, it was 24 square minus 13.5 square, it's ln Ri. I guess we have evaluated in previous part, 243.9. Yeah. And initial R note it's given. Initial R note is 105.88. So yeah, I guess if you calculate this, so this R note 105.88 was given, and yeah, so the R note is the equivalent radius of the excavation area. So yeah, equivalent radius of excavation area is given as 105.88. We have evaluated in the question number 7. You can check that. So for the whole excavation area, like how much is the equivalent radius? So that is 105.88. And if you can calculate this, how much you are getting, guys? I'm getting a 0.018. Yeah. So answer is 0.089 meter. So yeah. Any query in this? Okay. Let's go to the final. Let me solve it for you. So right now we need to calculate the discharge for each well. So what was happening, initially we was taking the whole area under the influence. So this rectangular region you converted into the circular part, and you were evaluating the discharge of this whole circular part. Now what's happening is you are dividing this circular into different small well points. So this can be any number of wells, but only information is given to you like this well point is having the diameter of 200 mm. So right now you need to evaluate how much is the discharge which is going to be passed through this each well. So same formula we are going to use. So pi into k into h w minus, sorry, hw not hw square ln radius and the influence. The only part which is going to change is the equivalent radius. So right now you are considering the equivalent radius for this whole circular part, but now since only one well is under consideration, so you will consider this one well. So it's having the diameter of 200 mm. The equivalent radius for this will be the 100 mm. So yeah, that is the part. So 100 mm if you take, it will be the point 1. So yeah, let mention radius of the well point. So if I just put the value into this, pi into 6 into 10 to the power minus 5, it's 24 square minus 13.5 square ln radius and the influence is given, I guess we have checked into the previous question, is 243.9. So equivalent radius is zero point 0.1 meter. So let me calculate it for you. 5 into 6 into 10 to the power minus 5 into 24 square minus 13.5 square. So yeah, I guess we are getting it as 0.0095. So yeah, option A is the answer. So done with our last question. Guys, any doubt in this, any part? Though I rushed through last two questions, but we can have a discussion on that, no problem.
Sir, I have joined late. Will you please, sir, from the very first question to question number six, sir?
Yeah.
Thank you, sir.
Hemant, anyhow this video is going to be uploaded on YouTube channel and those link will be shared with you through the NPTEL team. So I guess you can watch the whole video, like this video is recorded.
Okay, sir. Sir,
But
but I am unable to get the link of this video because from the very first video I never get that link.
uh, so I guess the NPTEL team is sending the mail to every individual who is enrolled into the course, and in that
Sir,
mail,
I get the link of PDF of this video
yeah,
in which all the solutions are given only after the completion of the assignment, sir.
okay, after completion of the assignment you are getting, is it?
Yes, sir.
So yeah, you are having, but you are able to access that YouTube channel, right?
Sir, I don't have the access of that YouTube channel, sir,
Okay.
in which solution is going to be discussed.
Actually, this is not the uh, assignment problems. These are the sample problems which
I
are going to help you in your
I know, sir, but I am not getting these problems because so that I can do the problems from the assignment, sir.
Okay, so no problem. I'll mention my YouTube channel here, so you can see the video. No problem.
Okay, sir. Thank you.
Yeah, yeah, no problem.